Today we're going to talk about power in electrical circuits. We're going to start by looking at a very simple circuit with a single cell and a big long wire and then a resistor here, and we'll loop it back up again. There we go. And we've got the negative terminal of the cell there. So which way do the electrons move in this circuit? I like to think about electrons rather than the direction of conventional current, because I can think about what the actual particles or the electrons are doing. So they're going to be repelled from the negative terminal and attracted to the positive terminal, which means they're going to be moving this way through the resistor there. So there is an electric field across this resistor. And we can draw the electric field in there. Again, plus and minus, that's the way the electrons are being attracted to the positive and repelled from the negative. So what we have here is a situation of a charge moving in an electric field. Of course, what do you get when you have a charge moving in an electric field? Well, work is being done on this charge. And we know this from the work we did with electric fields. If you remember back, you'll recall that the potential difference, V, in an electric, for a charge moving electric field, is equal to the work done on that charge per unit charge. So it's the work done per unit charge moving it in an electric field. We can rearrange that and find that work equals the potential difference times Q. Just going to shift this up a little bit. So of course the work done is a measure of the change in energy, potential energy, and we know that the work done is, in a simple circuit like this, it's the thermal energy being produced, or in a more complicated circuit with more sophisticated components, it would be the work done by the electrical components. Right, let's get back to these beautiful equations. What is power? Power is energy per unit time, or we can write it as the work done per unit time. And we can simply substitute this expression for work into the expression for power, and we get the potential difference of voltage times Q divided by the time. So the time it takes for a charge Q to move across a certain potential difference. Just rearrange this in a very simple way here. It's the voltage times Q divided by T. So the amount of charge per unit time. Does that look familiar to you? It should. And I'm sure you're thinking right now, aha, charge per unit time is simply current. And so this is an expression you'll become familiar with, where the power is the voltage times the current. Move that up here. We can do another nifty thing here, just to find a couple of other expressions that might be useful. We know from our work with resistance is that resistance R equals the voltage or the potential difference over I. So a resistor of resistance R with a potential difference applied across it of V, and you'll see a current I moving through there. And if we substitute that into there. We can find two other expressions for power, Ri squared and V squared on R. And that's just simply by rearranging this expression here. I'll just do a couple of very simple examples. These are straight from your textbook. I'll leave those equations there for now. A resistor of resistance 12 ohms has a current of 2 amps flowing through it. How much energy is generated in the resistor in 1 minute? And we can do this just by using one of these already manipulated equations up here. So we've got resistance and current, so we know that the power is the resistance times the current squared, which gives us 12 ohms times 2 squared, or 4 amps, which is simply 48 watts. In 1 minute though, so this is per second because the current is always in coulombs per second. I should write that over here. This is coulombs per second. So that's the amount of energy, or the amount of joules per second. I could write that here, joules per second. So in 1 minute, would just be 48 times 60, which you'll find to be 2.9 by 10 to the 3 joules. All right, another question. So this is our second question. A light bulb rated as 60 watts at 220 volts has a potential difference of 110 volts across its ends. So what that's saying is that, well, in general, in Australia, say, we have a voltage of around 230 volts approximately that we receive as our supply, and a light bulb rated at 60 watts would be producing that much energy per second, 60 joules per second, given a voltage of 220. So we can say when the voltage is 220, the power produced is 60 watts. It's talking about another situation now where the voltage is 110 volts instead of the 220, and we need to find the power dissipated by that. We can let the resistance of that light bulb be R, and we can write an equation for each of these situations to combine the power, voltage and the resistance. And that equation that we're going to use, we saw before, was power equals V squared on R. Right, so for the first situation, we've got 60 watts, power of 60 watts equals 220 volts squared over our unknown resistance R. And for the second situation, we've got a power unknown P is 110 volts squared over our resistance R. We could, of course, work out what R is over here and then substitute it into the second equation. But a little trick that we can do, and I'm just going to shift this up, is to divide one equation by the other. So let's put the left sides of the equations over, so the 60 watts divided by power P, and 220, the right sides of the equations now divided through by each other. You can cancel out the R and rearrange to find that P equals 220 squared divided by 110 squared times 60. And if you do that calculation, you'll find that is 15 watts or 15 joules per second. And that's our two examples